Hey, it's my great pleasure to introduce Tom Mitchell. Let's see, Tom, you're the Fredkin University professor now at CMU. Tom was my advisor many years ago. To give you an idea how long ago, back then a large neural net had one hidden layer and 16 hidden units and took days to train. So quite different from today. Let's see, so Tom, you formed CALD, the Center for Automated Learning and Discovery, and was the first director of that. And then later, I guess you formed the Machine Learning Department, which I guess is the first academic machine learning department, and we're director of that. Tom's currently here on the West Coast. I think you're on sabbatical right at Berkeley. So you wrote, is it the first textbook that has machine learning as its, I mean, I guess Duda and Hart in some ways is like an ML textbook from decades earlier, but Tom wrote really the first textbook in machine learning, a very popular book, which is still available. So Tom's done an awful lot of different projects, and we have to give him credit. He gave a talk this morning already over in CCP on NEL. This is that lifelong learning agent that learns from reading the web. So that's a really fascinating talk. If we don't have a recording of it on Skype, you can probably find other recordings. It's really fascinating work if you're not already familiar with it. And then what he's going to talk about this afternoon is new work that I haven't seen before, so this will be a lot of fun. Just one thing, I almost brought in some pictures from a long time ago at your lake house when we used to have machine learning retreats. We have pictures of Tom flipping pancakes for us and things like that. But I just wanted to say, Tom was my advisor, fantastic advisor. He gave you just that right amount of sort of independence and freedom to sort of make mistakes and get things right, and yet was sort of in the loop to make sure that you were making progress and that things were going well. So Tom was an uber thesis advisor. Okay, with no further ado, let me turn it over to Tom. So,
thanks, Rich. It really is fun to be here. I won't repeat, but this morning I gave a talk and I took a poll of how many people had taken classes at CMU, and I was very pleased with the response. But it's great to be here, and I should say something embarrassing about Rich in return.
I'll turn your mic on after you say it.
Okay. And that is the most embarrassing thing I could say about Rich. He also taught me how to look at the stars the right way. That's a true thing. But today, so here's what I'm going to talk about. We're at a really interesting point in the development of AI, because 10 years ago, computers, just 10 years ago, before the iPhone came out, 10 years ago, computers were blind and deaf. You couldn't really expect them to recognize anything in pictures. You couldn't really expect them to understand what you're talking about. And today we talk to our computers, our phones, all the time. And I think we're all underestimating the significance of computers going from being blind and deaf to being able to actually perceive the world on their own. If you think about the research that AI did when computers were blind and deaf, yeah, there was research in robotics, but it wasn't very effective. Most of the significant research was about thinking hard and not having to look at the world. It was about how to beat the human chess player, human chess champion, and other kinds of optimization problems. But now it's a whole different world. Now that computers can see and hear, it opens up just a whole new array of things that we can do with computers. And what I want to talk about today is one of the implications of that for machine learning. Because if you think about the future of machine learning, it's actually, I think, very simple. The present of machine learning is very straightforward. 99% of machine learning in practice assumes you have passively acquired big data and you apply some statistical machine learning approach to it. Maybe it's deep networks, maybe it's probabilistic models, maybe it's support vector machines, but that's the template. If you want to know the future of machine learning, all you have to do is think about ways in which we learn that computers don't yet. And there are lots of those things, right? We learn from instruction. You're here because I'm giving a talk, and hopefully you're here hoping to learn something. We learn from demonstration, from experimenting. We learn in a lot of ways that computers don't yet. And back to the first point, now that computers can see and hear, conversational interfaces are a very hot topic all around the world. But one angle on that I want to talk about today is, what if those conversational interfaces were used to let us teach our computers what we want them to do? And one motivation I have for this is the assistant that I have in my phone, whether it's Siri or Cortana or Google Now, those assistants are very different from the human assistant that I have in back at CMU. Think about some of the differences. One of them is that the conversations that I have with my agent in my phone are very short-term targeted conversations, like, is it going to rain today in Seattle? And I get the answer. The conversations I have with my human assistant are very different. It's like this. I walk into her office and I say, this fall I'm going to be teaching the machine learning class. They're going to be over 400 students. There are going to be 8 teaching assistants. I'll forward you an email to those 8 so that you have the contact information, and I'll also send you the URL for the course webpage so you can track what's going on. That's the first part of the conversation I have with my assistant. It has nothing to do with asking them to help me. It's just giving background information. And then I say, because I've given that background information, I say something like, and here's how I want you to help. Whenever there's a homework assignment that we're going to hand out, make sure that somebody gets it pre-tested, one of the teaching assistants, pre-tests all the questions 24 hours before we hand it out to the students. And whenever a student sends an email about a question, some confusion about one of the homework questions, make sure it gets routed to the teaching assistant who actually authored that question, who's responsible for that question. So the conversations I have with my human assistant are more like two-stage conversations. First, I invest some time just teaching her about this activity, the task that we're talking about here, the team of people involved, the documents associated with that activity where she can, in an ongoing basis, find information. And once she has that background, then she's in a position to actually accept requests from me of the form, if this happens, I want you to do that. If this happens, I want you to do that. And so I think it would be wonderful if I could have that conversation with Cortana. I can't have it today or with any of the other agents out there, but that's kind of the aspiration, is what would it take to do that? Okay, so now I have to fess up, we have not solved that problem either. But what I want to talk about is a project that starts to explore that problem. So here's how I want to frame it. In general, I want to say, suppose I have a robot-like system that is a sensor effector agent. In our case, the sensor and the effectors are going to be the things you find on a phone. Some of them are physical sensors like microphones and cameras and GPS detectors, accelerometers. Others will be cyber sensors. What are web pages out there on the web? What are the incoming messages? And there will be effectors as well, things that are actuators that can change that external world. Again, some of them are physical. The phone can vibrate or speak or display. Some of them are cyber. It can also send electronic messages. But in general, I want to frame the problem. Imagine you have a sensor effector agent that you want to learn from human instruction. And now think about the sensor effector closure of this system. By that I mean, if you have an agent with these sensors and these effectors, and you imagine you could put any conceivable piece of software connecting those two, then what are the operations that phone can do in the world? And the truth is, even phones today have an amazing set of sensors and effectors. They can do an amazing number of operations, rivaling what my human assistant can do. I mean, she can water her plants, which the phone can't do, but most of the things that I actually ask her to do are within the sensor effector closure of the phone. And so there's a tremendous scope of tasks that, in principle, given the right software, would be within reach of a phone with just its current sensors and effectors. And for example, it could handle this. I could say to it, whenever I have to catch a flight, alert me to head to the airport so I'll arrive before the flight takes off. Now, fortunately, Google engineers somewhere along the line already thought of that one. And so my phone already reminds me when I'm heading to the airport. It's a useful thing. But there are many, many other things that I'd like to ask my phone to do that the Google engineers haven't yet, and the Microsoft engineers and the Apple engineers haven't yet put in my phone for me. I live in Pittsburgh. Whenever it snows at night, set my alarm 30 minutes earlier. I want to get to work on time. If somebody sends me a picture containing my mom, forward it to her. She likes them. And forward means, in her case, email it. Whenever a student sends an email about a homework question, forward it to the right teaching assistant. These are all things that are within the sensor effector closure of my phone. And if I had the right software in there, it could do it. If I wait for Microsoft or Apple engineers to implement it, I'll be waiting forever. It's not because you guys aren't great. You're great. It's just that you don't really, this is an idiosyncratic thing that I want my phone to do. It's not a universal thing that you all want your phones to do. Same with this, maybe. So the point is, a lot of the things that I want my phone to do are never going to be, hopefully never going to be implemented as a mass market thing that everybody should have. A lot of them are really about my personal idiosyncratic situation, the tasks, the teams, the times, the places I'm involved in. And so I'm willing to, and I want to be able to teach my phone about these kind of things. So that's kind of the structure of it. Okay, so to be a little bit more precise about the problem then, I'm interested in the question of, if I'm given such a sensor effector system, and it has a primitive language capability, by which I mean it has an initial lexicon that allows me to refer to all of the primitive sensors and effectors. If the phone has an accelerometer, then the primitive language capability should include me being able to say, what's the reading on the accelerometer? And it should know what that means, and it should be able to respond. If it has a primitive effector like buzz or vibrate, then I should be able to say vibrate, and it should vibrate. So that's the primitive language capability to invoke those. And maybe there will be other needed language capability. Maybe it'll need to know about arithmetic and logic and things like that. So I'm not saying it shouldn't have other things, but it will at least need to be able to allow me to refer to its sensors and effectors. And then I wanted to learn these things. Several things. One is I wanted to learn the language, better language. Maybe it knows what I mean by send this email, but maybe it doesn't know what I mean by drop a note to Bill. I wanted to be able to learn that language because it'll be my language. I wanted to learn the capabilities. If I say drop a note to Bill, I wanted to know how to do that, how to do that. I wanted to be able to be instructed how to do that. And I wanted to be able to learn representations of my life like I'm teaching a new course, or I'm oh, you don't know about courses. They're activities that have people and students and so forth. I want to be able to learn that. Okay, so here's the outline of the talk. Let's talk about, we just talked about the problem. So let's talk about teaching new commands, and we have a little prototype system that sometimes that I want to talk about. And then teaching about a new command like drop a note to Bill. But then move on to teaching conditional strategies. If this happens, then I want you to do this. And then teaching by demonstration and kind of wrap up. So for teaching the system, here's the kind of overall philosophy that we're taking. We just want it to be the case that teaching an agent to do something is just like you teaching me to do it. You should be able to use the same verbal language and demonstration that you would use if you were teaching me. One reason we want that is that's what people already know how to do. If we could get phones and other devices to be able to accommodate the way people naturally teach each other, effectively we make every single person on earth a programmer. And then they can program their idiosyncratic, quirky things that they want their phone to do without waiting for smart engineers at some other company to guess what they want. Anyone should be able to teach both verbal instruction and demonstration, and whenever they feel like doing it. Okay, so let me show you a video of a prototype system we have. What you're going to see here is our postdoc, Igor Labatov, who has done a lot of this research, teach the phone to do something. He's going to give it a command. The phone won't understand what the command means. And then he will go through an instruction sequence. When he's done, the phone will have learned how to do that, but it will also, at the same time, learn a new language competence that allows it to understand that command and different uses of that command. So here's the video, and I think we have, the audio will work fine. Okay. So I'll just play this, then we'll review it.
Tell Tom to come to the meeting a few minutes early.
Sorry, but I don't understand. Would you like to teach me? Say yes or just ignore.
Yes.
Great. When you say, for example, tell Tom to come to the meeting a few minutes early, what shall I do first? Either tell me what to do or say demonstrate to demonstrate.
Create a new email.
Composing new email, outgoing email, fields are, subject, body and recipient list. What shall I do next? When executing, tell Tom to come to the meeting a few minutes early.
Set the recipient to Tom's email address.
The recipient list field in outgoing email was set to tom@gmail.com. What shall I do next? When executing, tell Tom to come to the meeting a few minutes early.
Set the subject to please come to the meeting a few minutes early.
The subject field in outgoing email was set to please come to the meeting a few minutes early. What shall I do next? When executing, tell Tom to come to the meeting a few minutes early.
Send it.
I see that the message has no body. Email sent successfully. What shall I do next? When executing, tell Tom to come to the meeting a few minutes early.
That's it.
I'm currently learning the new command, tell Tom to come to the meeting a few minutes early. I'm trying to generalize to other similar commands. This takes several seconds.
Tell Bob to bring some coffee.
Composing new email, outgoing email, fields are, subject, body and recipient list. The recipient list field in outgoing email was set to bob@gmail.com. The subject field in outgoing email was set to please bring some coffee. I see that the message has no body. Email sent successfully.
Okay, so So what did we just see there? So he said, tell Tom to come a few minutes earlier. I'm running late, I forget what he said. And the system didn't understand. And so he spelled it out step by step. Create a new email, use Tom's email address. Here's what goes in the subject line, send it. So he spelled it out in terms of the primitive sensors and effectors that the phone does understand, and in language that it could understand. And so now at the end of that, it knows what the semantics was for tell, whatever it was he said, tell Tom I'm running late. So now it knows what the semantics for that was because it just executed it. So it learned both what the sequence is for doing that operation, but it also updated its language lexicon so that he could then say, tell Bob to bring some coffee. And it didn't have to ask him what that meant because now its language competence had extended so that it knew what tell a person something meant in terms of semantics grounded in the sensors and the effectors of the phone. So what it learned there was both the procedure, the sequence, and the language competence in a way that, in this case, generalized to telling Bob to bring coffee and tell person to X. Okay, so that's the kind of thing, kind of competence we're interested in. And what I want to do is first show you what's under the hood, how this works. So this system is built on a CCG parser. What I should say is that the first version of this was built, the version that I just demoed here is built on a CCG parser, and now we're exploring some alternatives. But in all of the alternatives, the key is that the meaning of an utterance is represented, the semantics is represented as actually a Lisp expression, if you're a Lisp fan, but a logical expression that can be evaluated. And when it's evaluated, it executes the command. Okay? Yes?
Are you interested in taking questions as you talk, or just a few?
Let's try one.
Okay. So I understand the motivation that you want to be able to teach it in language, but have you guys run into cases where it would be easier to do it through some GUI? And in those kinds of cases, would you still prefer to do it through language, or can you imagine?
Yeah, we have seen cases where a GUI is better. I have my second movie is the demonstration version. And what we don't have is something yet that puts them both together. But you're absolutely on target that sometimes demonstration is easier than verbalization. But we think in the end you want to be able to do the two. That's how you would teach me if I asked, how do I order a Starbucks cappuccino? You'd tell me and show me at the same time. Okay, so the way this works underneath is built on a CCG parser. I'll say more about that. The parsing steps in a CCG parser, for example, like all parsers, combine some primitive things into a higher level token, like an adjective noun should become a noun phrase. But in the semantic parsers we're considering, there's a simultaneous step where the meaning of the adjective and the meaning of the noun get composed to be the meaning of the phrase. So perhaps like pink taxi would turn into the pink function applied to the taxi, and it would be true or false. The learning by instruction agent, Leah, executes the meaning of the sentence, and since those are grounded in the sensors and the effectors, it executes the command. And it learns from examples by redefining the grammar, adding new lexicon entries, and also relearning the parse strategy. The grammar isn't enough because there will often always be multiple parses of the sentence. And so it has to learn both by adding new entries to the grammar and by retraining its heuristics for selecting the right parse. So take an example. Let's consider this expression, set the subject to time to go. Suppose I'm instructing the system to send some email and I want the subject to be set to time to go. The CCG grammar is shown down here. I'm not going to go through all the details, but just a quick example of parsing means that, for example, one interpretation of subject is that it could be referring to a field name, like the subject field of an email. So that could be a parse for the token subject. And then it can be further, the semantics for that can be turned into this expression, which basically gets the subject field. Take time to go. One interpretation of any sequence of tokens is that it's simply a string that should be captured. And then the preposition to for that can be consumed in the CCG parse to be a prepositional phrase string. And then the can be simply removed. In fact, any token, one possibility is to just throw it away in our grammar because that makes parsing easier. And then the verb set can be interpreted as, it's defined this way in CCG grammar, but basically the meaning is that it's a set field from string is one possible meaning interpretation for the verb set. So by the time it's done, one possible parse, the right one in this case, is that string got parsed into this logical expression. So it's okay if you don't understand all the details of CCG grammar, but you see what's going on is that the pieces of the sentence are being consumed by the parse and converted into semantic expressions so that at the end we have this one. And there are many possible parses, so as I said before, part of what has to get learned is the heuristic for guiding the parsing strategy so that we get the intended parse. Okay, so now from that, in the example that we just saw in the video, the semantics for tell, which were not known initially. That's why the system said, I don't understand what you mean when he said, tell Tom I'm running late, whatever he said. Tell Tom I am late. The learned semantics now at the end is this for the verb tell. How did he get it? Because when it said I don't understand, he said, well, create a new email, put the subject field to this, put the recipient field to that. And those steps turn into an expression like this. Do this sequence. Create an instance of an outgoing email, set the field, the recipient list, the email address, and so forth. So this expression comes out of the sequence of steps that he spelled out and could be spelled out by demonstration instead of verbalization. And there's some generalization that happened here too. The generalization heuristic that we use is that we parameterized any text span in the original utterance, like tell Tom I am late, any text span whose semantic parse is a subtree of the full sentence semantic parse gets parameterized. So in this case, the text span I am late ended up being a subtree of this tree, and therefore it got parameterized here into this parameter. And similarly, the email address got parameterized. So hence we end up with this. So this is a heuristic for doing the generalization, but we found it to be actually a very commonly useful heuristic. So hopefully that gives you the picture. So then we train the grammar. So what we just saw in the previous slide there was how a new entry, say for the verb tell, gets added to the grammar. So now this becomes a new entry in the CCG grammar. The word tell can have this semantic expression associated with it. And then of course we still have to train the system to select the correct parse out of these grammar rules. And so we have a number of labeled examples that we provide and other labeled examples that come in over time as users train the system. And we use those along with to retrain the grammar at each step. So that's the approach. We did some experiments on Mechanical Turk with a typed text version instead of spoken with this system where we got subjects to interact with the system. We gave them a mock email environment to work with, and we give them tasks like this one. This says, your task here is to create a new email and set the recipient to the current email sender. And don't type the email yourself, just use current email sender as the phrase. So we gave people these kinds of tasks, and you see the user said, set the recipient to mom, and the agent said, sorry, but mom is not an email address. And so the user said, set the recipient to mom's email, and so then that worked. And then they go through, set the subject to hello, and send the email, read the email. So it's this kind of interaction with the system, and they're running into cases where the system does and doesn't understand. They have the same opportunity to teach or not teach when the system doesn't understand. And what we found was that of the subjects who completed the 25 tasks we gave them, which was only 41% of our subjects, but of those who did complete, many of them voluntarily taught the agent simple commands that they then reused, and they did save them time. Here's a little bit more detail on the experiments. So the commands that they did teach did save them significant effort. The completion rate, as I mentioned, was a problem. More than half of the people bailed on us before they got through the 25 tasks. There were some parsing failures, execution errors, and so forth. But in general, well, this speaks for itself. I don't have to say more. So that's kind of what I have to say about the basic problem of simultaneously learning a procedure and a language competence to refer to that procedure. There's much more to be done there, but I think the sketch of this idea, the good ideas in there are that the semantic parse grounds out in the sensors and the effectors of the agent. That's a good idea because that means really everything that's in the sensor effector closure, everything that's doable by the agent is within the scope of what you can talk about. And then the other good idea is you need to learn language competence in parallel with teaching procedures to the system. But what that example doesn't show is how you would teach a conditional thing. Like, what if I want to say, if it snows at night, wake me up 30 minutes early? And there are a whole set of issues there, including the fact that I don't really mean to wake me up 30 minutes early whenever it snows at night. What I really mean is, if it snows at night, wake me up 30 minutes early because I don't want to be late for work. That's what I would say to you as a person. And then you would know, well, on Sundays I won't worry about it. If it's a snow flurry instead of 3 inches of snow, I won't worry about it. And for me to actually instruct all the corner cases, if it snows, but not if it snows half an inch, unless there's an ice storm also, it would take me forever. So there are some serious issues about, for some of these conditionals, how you would actually teach them. And so, but we have begun to look at that. And so here's some examples, right? Whenever I'm stuck in traffic on Forbes Avenue on my way to a CMU meeting that's less than 20 minutes away, alert the attendees that I'm not going to make it. So now you can think, in that previous example, we were using language to talk about commands. Now we want to talk about conditionals. And if you start taking that apart, you notice there are actually several types. I could say, for example, if I get a new email from Fred, then do this. That's an easy case because I can use language to define what I mean by that if condition. I can dictate a procedure to you. Let's just look at the from field, and if it equals FRED, then this condition is satisfied. But if it snows at night, well, I could, again, demonstrate. I could say, well, you have to pull up the weather app. You have to look at the current conditions, and if that equals SNOW, then it's snowing. Oh, and if it's night, that means the time is between the sunset and sunrise. So I could do that. I teach it as a procedure. But then the hard cases are like if I get spam. Because even though I know it when I see it, just like I know my mother when I see her, I can't write down a procedure for a computer to recognize either my mother or spam. So it's a competence I have which I'm not able to declare, put down declaratively. And so when you start thinking about teaching conditionals, you get into a number of these issues. And the hardest one is this, if I get spam or if I get an email that's important, or if a lot of these sort of non-crisp concepts that we use all the time to talk about with each other. Part of the reason we do that is we all have common sense, and so if I say, if it snows at night, wake me up early, you know what I really mean. And if I say, if I get an important email today, be sure I see it before I give my talk, you know what that will mean, because you have common sense and you can think it through. So computers may need that in the long run, but in the shorter run, we have and I should say this is the work of Shashank Srinivasta, one of our PhD students working on the project. He got interested in those kind of difficult to dictate conditions. It's really a concept learning problem, right? If the state of the world satisfies is a member of this set, if it's spam email, for example, it's a concept learning problem, then do that. And so he got interested in, well, maybe we could look even deeper into natural language instruction and see if we could get people to think of a system where they could teach what it means to be spam, even though maybe they can't teach perfectly. So they'll have to combine some examples with advice. So here's the way we set that up. Suppose you want to learn a classifier, like I say, if it's spam, then throw it away. And I'm given a small number of labeled examples. Here are some emails labeled as spam or not. I'm also given a set of natural language statements which refer to Boolean properties. Like I might say, well, if it's trying to sell me something, it's probably spam. If it's offering me money if I submit my bank account, it's probably spam. I would make those kind of statements if I were teaching you what I mean. And so we assume we're also given a set of those which the system doesn't necessarily understand, along with the labeled examples. And now we wanted to output a semantic parser that learns the meaning of these advice-giving features. You can think of this as a feature. It's its own predicate. It's its own feature of the X's of the email. It's just that it's only defined by this natural language string. But the user is telling us this because they believe this is a property of the X's that's relevant to predicting the Y's, predicting that it's spam. And so now we want a semantic parser that will understand, make sense of what these strings are, and also a classifier that learns to predict the Y's from the X's. So that's the problem Shashank has been looking at. His approach is we'll represent each of the X's that we're trying to classify. Let's say email, and we're trying to classify it as spam, both by the observed features. We can see the bag of words that are in the email. We can see who the sender is and so forth. But also by a set of n features corresponding to these n sentences whose values we really don't know because we don't understand those sentences necessarily. Some we might, but in general, we might not understand some of those n sentences. So we're going to represent x as a feature vector where there are the usual observed features, but also a set of features whose values are not initially known, and then use expectation maximization algorithm to simultaneously estimate the values of those n features that we don't know, and the classifier based on those n plus the observed features to do the labeling. So you get the idea. We're going to iteratively estimate what the Boolean value is for these sentence features, and then estimate the parameters of the classifier, assuming those sentences have those Boolean features, and iterate. And then if we can get that, that'll also interleave with using those inferred meanings of the advice-giving sentences as the basis for updating the grammar, the parsing strategy. So it's kind of three things being learned here. One is the classifier itself. One is the values of these features, like if it's trying to sell me something. And then the third is the parser. So we went to Mechanical Turk and generated a bunch of emails. We had people write emails and label them according to these categories, like you're writing an email to yourself as a reminder to do something. We have 154 such emails labeled as reminder emails and so forth. Then we got other Mechanical Turk workers to give us advice on how you would classify, if you're teaching a person to classify those. And then we ran this EM-style algorithm and found that here you see two curves. The red one is if you ignore the user advice and just use the labeled examples, number of labeled examples, to classify the emails into those 6 or 7 categories I just showed you. And then the blue curve is if you also use the advice and this EM process to estimate the Boolean values of each advice thing for each email and the classifier. And so you see that we're getting some leverage out of that advice. So again, this is very early work, but again, the theme that I want to try to get across is that there's a language learning problem interleaved with in this case, the concept learning problem of learning the concept of the antecedent for this command. If it's spam, then we have to say, how would I recognize spam? Now we're getting natural language advice for that concept learning task and trying to use it in this EM framing so that we simultaneously learn the classifier we're after, spam, the inferred labels, values of those advice features for each email, and the associated grammar for making sense out of those. So again, there's a lot more to be discovered from this, but that's kind of what we've been looking at. All right, so you asked a great question before, which is, aren't there certain cases where teaching by demonstration is better? Brad Myers and Toby Lee, his student, and Amos Azaria, one of our postdocs who recently graduated into professorhood in Israel, have developed a teaching by demonstration thing they call Sugilite. I asked Toby for a 1-minute video, and he's really smart, so he took a 4-minute video and he sped it up. So you have to watch very closely to this. But you'll see him use his system to order a cappuccino from Starbucks and then show it generalizing to another example. And here's the video.
Order a cappuccino.
Sorry, but I don't understand. Would you like to teach me? Say yes or just ignore.
Yes.
Great. When you say, for example, order a cappuccino, what shall I do first? Say demonstrate to demonstrate.
Demonstrate.
Whenever the user gives the agent a command that the agent cannot understand or doesn't know what to do, the user can teach the agent by demonstrating how to perform a task using any third-party apps installed on the phone. In this example, the user demonstrates how to order a cup of cappuccino using the Starbucks app.
Order a cappuccino.
Executing.
The agent learns the task and is now able to automatically manipulate the Starbucks app to order cappuccino for the user. From only one example of demonstration, Sugarland can also determine the parameter in this task from the user's voice command and find all the other drinks it can order from Starbucks by analyzing the structure of the app's user interface. As you can see, the duck icon on the screen is now clicking on behalf of the user to order a coconut milk mocha macchiato. This work will appear in Kai 2017 and was supported by Yahoo through CMU's inline project.
Okay, so again, what you saw there was using demonstration rather than verbal commands to spell out the sequence of what we mean by order a cappuccino. And you saw that it basically, by analyzing the drop-down menus, it could see which of these things, it had to go to a drop-down menu to get to cappuccino, and there were obviously other choices. So the heuristic there for generalizing is to leverage those menus and generalize cappuccino to a parameter that could have any of those values. Which again, could work in some cases and not in others. Maybe if you click on a different choice on the menu, you'll be taken down a different route in the app, and the pre-learned sequence of steps for follow-on won't be the right one, so it can fail. But again, this is the experiment that's underway. So and I should say that one thing that's very nice about this system they've built, we basically have our own version of Android now that we can get every button click and so forth. So as a result of that demonstration, the user gets to see this learned script for send email or for order a Starbucks coffee, and the user can go in and effectively edit or kibitz on which would be a parameter as well. We still don't know what the right strategy is, but this is kind of the substrate on which we're trying to build this ability. And here are some of the things that they've programmed the system to do through this kind of demonstration. So here's my final slide. So I think the point is obviously, let's explore a kind of learning by instruction, even though learning from statistical big data is a very valuable thing for us to do. It doesn't really cover all kinds of learning that we want computers to do. In particular, it's, in retrospect, looking back, it's kind of strange that almost all of the learning that my phone does about me is based on the idea that it should sit back and not pester me and just observe passively what I'm purchasing on Amazon and other places, and then after it has enough examples, try to help me. If my human assistant did that and just committed to passively observing me and not bugging me, she would have been fired years ago, and so would have I. It's just not an effective strategy for a lot of the things we want to learn. So we really need this kind of competence if we want to move mobile devices and other kinds of computer equipment beyond the limited kinds of learning that they do now. So basically, here are some directions. We want to integrate verbal instruction with demonstration. We don't know how to do that. We are running some new mechanical Turk experiments, collecting data where people are asked to demonstrate and to speak out loud while they're demonstrating, as they would if they were teaching a person, just to try to get an understanding of what people say when they demonstrate. Like I might say, now I'm choosing the cappuccino, but there's a menu here, you could choose other things, obviously. Or now I'm paying with a credit card, but I could have used Apple Pay. So we're starting to get some data about how people combine demonstration and verbalization. There's a very interesting question of if we have this capability, what's the right strategy for aggregating what gets learned across users? Many interesting questions there. If I teach it that there's such a thing as a academic course, I didn't point this out, but another thing you can do to the system is you can actually say to it, create a new concept called academic course. It has fields, instructor, students, website, and so forth. And you can declare those things in our system, and then you can refer to them as you're teaching it. But so what should be shared? Maybe if I define what a course, academic course means, that should go into the public part of the ontology, because why would everybody want to define the same thing? But if I define what I mean by friend, it might be different from what you mean by friend. Or there, you know, we all have our own parts of our personal ontology that should not be shared. What about incremental refinement? When we teach each other, we actually, you know, later I might come back to you and say, do you really mean if it snows or if it snows a lot? And whenever I try to think that I've taught you an if-then thing, I've actually probably left out details. No, I didn't mean on weekends. I just forgot to say that. And so what does that incremental process of refining the instruction look like in a successful system? What about mixed initiative teaching dialogues? Right now, there was a conversation, but and it was mixed initiative, but it was pretty constrained mixed initiative. It wasn't the open-ended kind of mixed initiative two people would have with each other. I think actually instead of teaching conditionals if-then, we should really be teaching if-then because. And that will open up, like, if it snows at night, then wake me up because I don't want to be late to work. Now, if you have some general background knowledge, you can fill in for yourself the way a human would. What I really meant by if it snows at night. What I meant was if it snows enough to interfere with the traffic, to delay me getting to work, then wake me up. And so if I can say what the goal is as well, I open up the opportunity for you to use your background knowledge to guess what I really meant, even though I was being terse, as we always are. So then combining all these things. We also need some theory. We need to understand, we have these great statistical learning theory results about sample complexity of different kind of learning algorithms, how many examples it takes to assure a certain quality of learning, if those are labeled or unlabeled examples in different settings. We need to extend that kind of theory to handle instruction. What does that even mean? How many example labels or demonstrations or suggested new features? We also need a theory about agent architectures that talks about questions like, if we have an agent that's going to be learning on its own over a long period of time, what are the sufficient conditions to assure that it doesn't damage you or it along the way? What are sufficient initial capabilities to assure that it'll be able to learn everything in the sensor effector closure? Surely it needs an initial ability to refer to the sensors and effectors, but probably it needs some knowledge about logic, arithmetic, constancy over time, various things that in addition to that. So I'll end there. I think you've probably picked up on the idea that this is fairly new work for us, so that we have more open questions than we have answers. But I think this first step that we've taken has some of the traits that we would like to have in the future. And I think these kind of problems are central to Microsoft going forward also. I mean, Microsoft in some sense is all about personal tools that get customized either to individuals or to enterprises. And if you open up just the question of if future versions of Microsoft software could actually have this kind of instruction from their users, what would the user want to instruct, and which of those things are actually within reach in the next couple of years? So I hope to have some discussions over the next couple of days, getting your ideas about that. Thanks.
Definitely time for a few questions.
Yes.
First, I totally loved your talk. I was curious about the choice of CCG in the first section. And so there you're using CCG as a way of essentially mapping from text to a little computer program. Another way of formulating that task would be infer a little computer program from the sequence of actions that the person says to take, and then use some kind of general machine learning model to map from example utterances to that program. And I was curious if you thought is there something particularly attractive about CCG? Was it sort of used by default? What was the thinking process behind selecting?
Yeah, the thinking process was B. It was kind of used by default. Jayant Krishnamurthy, one of our recent PhD students, developed a CCG-based system that could be trained. And so we started there. We knew that we wanted a semantic parser that would produce semantics that were executable in terms of the sensors and effectors. And so we started there. We're currently experimenting. Percy Lang at Stanford has also a very interesting semantic parser tool similar to the kind of thing you're talking about. And so we're actually experimenting with that now as an alternative to this. The trade-off seems to be the following. CCG parsing forces you to account for every word in the sentence. You have to do something with that word. You either have to explicitly throw it away or combine it into the words around it to parse the sentence. And so you don't miss things. The other approach is more like word spotting. It's sort of like find words in this utterance that might refer to the things that to the semantics that you have, and pay attention to those and feel free to ignore everything else. So it's a question of whether, so you could think of it as a spectrum of you must, CCG, you must account for every word in the sentence as you're doing it, or no, you must account for every operation in the semantics, but not the words in the sentence. And so I think that's an interesting spectrum. If I had to guess what we'll be using 4 months from now, it's that end of the spectrum. Because conversations are so unstructured, people are so ungrammatical, they hem and they haw and they reverse and stuff. So that seems like a pretty promising direction. One problem we have had with that, though, is that I wish I could generate an example sentence for you. The phenomenon is because you don't have to count for every word in the sentence, you don't, and you end up getting crazy stuff. Like,
Classic example would be missing not.
for example, although we haven't seen any utterances where people use negation, but it was more like you would say, like you would have the phrase email address, but it would know it had an email, so it would pick up email out of email address, and it just get it wrong because it wasn't required to pay attention to any words it didn't feel like. So that seems to be a trade-off. But again, if I had to guess where we'll be 4 months from now, it'll be more on this side of the spectrum. That's a great question.
So, in many cases, if you want to complete a task, it's not just a sequence of primitives. Right? You need to learn things more like in a structured way. You say, oh yeah, this is a way to do a subtask, and then you build that up along that. But also this, pose a lot of challenge to learning. Because for a human, I need to know what has been learned by your phone or what has not been learned.
Yeah.
And then there's also a lot of human HCI things over there. You experience how to. What do you think? What is a what do you have any thoughts on those?
So hierarchical construction is happening in our current system. So if I say, drop a note to Ye, and it says, I don't understand, and I say, open up a new email and put Ye's email address in it. Now it knows what drop a note means. Then I can say, like, drop a note to all my contacts from Microsoft. And I'll say, I don't know what it means, but I can teach it then by saying, well, for each person in that group, drop a note to them. So you can refer to drop a note once it's in the lexicon, now you can use it, and it'll know to expand it to that semantics that you had previously taught it. So in some sense, language makes it easier to use as primitives the things that you originally taught, that you had previously taught. They become primitives that you can now refer to, like drop a note. But I mean, how you would manage that at scale, and how the user would know what the system could and couldn't do, that I'm less, I mean, who knows, but I'm less worried about that because I think users will do okay if they know the sensors and the effectors, and you tell them, and everybody does. My mother knows what her phone can and can't do, right? And she's not a computer scientist, but she's smart. That's why I keep bringing up my mother. And she would just say, she would intuitively know that it can't shovel her sidewalk, but it could communicate with other people. So I think she would just naturally be inclined to say stuff to it like she would to me. And if it doesn't know what drop a note to Tom means, it'll tell her. And then her option is either rephrase or teach. And so if she's in a hurry, she'll say, send an email to Tom. And if the system is smarter in the future, it would know that that rephrase probabilistically is the meaning of the thing that it didn't understand, but that's a different issue. So I think people will naturally restrict their language to the competences that the phone has. And if it has the primitives, if it has language competent corresponding to the sensor effector closure, then it's not impossible for the person to follow up by an instruction. And if it doesn't know, well, it's just like if I don't know what you mean when you say something and say, I don't get it. And then you have the option, you can teach me, but it's going to delay you, or you can just move on and say something else. So, I mean, that's just guess, because we don't have any HCI studies to back this up. Maybe people here do. Rich?
A question, instead about generalization, more specialization. So you had the example, tell Bob to bring coffee, and that became send email to Bob with this subject. And then suppose you want to, tell Mom, to make coffee, or whatever. And maybe when you communicate with your mom, you don't send an email, you text, members of your family, you might text. So now you want to sort of specialize this previous command to being, well, when it's somebody I work with at CMU, use email when I say tell, but actually when it's a member of my family, then tell means text. So how, if you had the first one, have you thought about how you would try to specialize? Would you have to create a concept of like family and friends different from employees, and then you would go in and specialize the rules somehow, tell?
Yeah, interesting. So in the current version of the system, actually tell can have multiple meanings. Every word has multiple possible lexicon entries. So tell could be send an email, tell could also be text. And those just become alternative semantic parses for tell rich. The place where the context that you're telling Mom versus telling Rich comes in is currently in the heuristic evaluation function that's getting learned for guiding the parsing And so it might say, oh, if it's tell mom, then it really is more probable that it's tell with semantics text. Whereas if it's tell Rich, it's tell with semantics email. So that could be part of what gets learned in the parsing strategy, which is looking at all the different words in the string. There may be more sophisticated ways than that to do it, but even in the current system, that's not off limits. And maybe, at some point, if you were a person, I would simply say to you, for my family, I usually use Instagram and or text them, and for my business people, I usually email. That's what I would say to you. And then you'd say, okay, or you'd say, well, then tell me who's in your family, or something like that. So, yes?
So on a follow-up question, I'm just wondering in the current UI design, if, for example, the system actually generalizes the wrong thing, or maybe it's a special case, just like Rich said, whether there's already some kind of mechanism to actually deal with this kind of fault-forward.
We don't have enough mechanisms, because sometimes you get in an awkward situation, but it never adds a new lexicon entry. It never, like if you say, I want to teach you, at the end it says, well then, here's what I'm doing in this instance, is this right? So at least you get to prove, what I mean by tell Bob I'm late is to send the email you just described. Yes, do that. What you don't get, and it's not clear how to do it, is the generalization that the system is doing. It doesn't try to communicate that to you. And it would, I think, be kind of, well, if you had it could say, and I'm parameterizing now Bob into any person, and I'm parameterizing I'll be late into any string. I guess you could have it do that, but it doesn't currently, and You're highlighting something that I think is really important, which is HCI and machine learning need to get a lot more cozy with each other than they currently are. At least, these two fields are going to blend together, and AI in general. And over the last couple of years, we've had this project to try to examine intelligent agents in phones, and it's been just a wonderful education working with the HCI people like Brad Myers, the guy who did the demonstration stuff, and learning how they think about the world. But a lot of these evaluation issues are probably things where HCI people have better insight than I do.
So you alluded already, I think, this in the future work or things you're foreseeing, but so my question is more about scalability. Like, do you envision this, like what do you envision the challenges if you try to look at this as learning a larger language, and if you try to overlay what different people sort of might teach the system? Because I think there's a number of things that start kind of going, like, there's aliasing in language. I might teach it the same procedure as you teach it, but call it something different.
Right.
There's discoverability issues that we already have in these interfaces. I don't know how many buttons and how many things I can say and teach. So I'm just wondering, like, I can see this running smoothly for a relatively small language that I would create personalized for my phone. But if I start thinking of this as a broader language where this thing becomes really knowledgeable, like I can kind of see some of these barriers, and I was wondering what your thoughts are on that.
First, I think it really is an important issue. We haven't thought deeply about it. We're struggling to get this to work for single individuals at the moment. We haven't even looked at sharing. I mean, I am struck by the fact that each of us as individuals talks with many people who have their own phrasings, and just as for the phone, you might mean something different from you mean when you say, be sure to let Bob know. I mean, do you mean call him? Do you mean send him a note? Do you mean if next time I see him, let him? And we manage. We manage, and maybe part of the way we manage is if you tell me that and I find it ambiguous, I'll ask you a quick question. So I mean,
Either are people hitting against trying to do repairs or anything like that in the systems as they teach it, or is it mostly smooth sailing at this kind of size experiments?
in the Mechanical Turk stuff, we did not give people the ability to delete things. But in the version of the system that is on the phone, I insisted that we have delete things because I found myself getting into situations where, even simple things like speech recognition error, it now thinks Rich's email address is some bizarre string that it misheard when we were playing around. So you need that sort of thing. More importantly, it's hard to remember what you've taught the agent and what it knows about you and what it doesn't. Maybe that'll be easier once we actually, right now this is a standalone system, so if I wanted to know about Rich, I have to tell Rich Caruana is a person, and here's his email address. But maybe if we tap into the other information on the phone, like the contacts list, then it'll be easier for people to have assumptions about what it knows. But still, once it starts getting complicated and they've taught it things and other people have taught it things that they're not even aware of, then there will be this issue. And the only optimistic note is we all managed to talk with a lot of different people and get by. Yeah.
So related problem, a related question to complexity of the system. What is your assessment of the complexity of the guided parsing in terms of number of sensors and number of concepts that you have in the system? And is there a danger there that as you're adding more sensing capabilities or more concepts, it becomes useless?
I guess I'm optimistic.
Sorry.
I think I'm optimistic about scaling the number of sensors and effectors because there's very little risk if I add accelerometer that my utterance to tell Tom I'm late is going to be misinterpreted as a reference to an accelerometer, right? So I think scaling by doing the complete set of sensors and effectors, and I should say actually in the system that I demoed here, the only thing we've tapped into is email and alarms. But we're working hard to get all the sensors and effectors, and I think
something like snow would be a sensor, right?
Yeah.
Yeah. So as you extend that vocabulary and you introduce traffic, and you say if traffic is greater or if traffic is higher today than yesterday, which part of traffic, which part of the map should I look at? When you talk about alarms, if you set your alarm for an afternoon nap, should I wake you half an hour again, or in that sense?
Yeah. So maybe you're right. Yeah, I guess that makes me think again that, the analogy to how people resolve these ambiguities. We just have a tremendous amount of common sense background knowledge that's shared. And so a lot of the ambiguity in what we're actually saying doesn't even feel ambiguous because that background knowledge, we know traffic is actually about driving cars and getting to work and stuff. And no phone right now knows that fundamentally doesn't know the way that we know what traffic is about. So maybe for this to really succeed, we'll have to have a lot more common sense in the. I mean, maybe that's one of the big questions here is how far can you go with language without actually having the background knowledge and the common sense to resolve the ambiguities? And, yeah.
I know that you're working with Igor Lavutov.
Yes,
And
that was his voice on the.
So while he was an intern here, we worked on question generation. So I wonder, when we talk to the people who help us, it's not a one-way. We don't just instruct them, they ask questions back.
That's right.
And so I think some of these complexity issues might be managed if we also developed a theory about which questions does the computer need to ask in order to disambiguate.
Yeah, that's really good. That's probably a key part of how we get by as people, right?
It's generally not recognized in the NLP community right now how important questions are to our conversation.
Yeah.
So,
yes.
I was thinking about the sensor effector closure and whether or not it's really well defined. Because it seems like with services like TaskRabbit or something like that, you can do just about anything. And as you add more services to the web, then the phone can do more and more. And so do you think that that's right? And do you think that there are, kind of, what's the use of trying to think about this closure? And the bullet point you have there about being able to do everything effectively, right?
Uh-huh.
I don't know. It seems like it's an interesting question as to whether there is a clear boundary.
Yeah, your point's correct that it's a moving target, because as more facilities go up on the web, like webcams, then even though yesterday you couldn't see this particular football field, today you can over the web because somebody put up a webcam. I think that's fine. The reason I like to think of it this way is that it makes more obvious the question, how complex a programming language do I need to support in terms of instruction? You know what I mean? So like, so I think the sensor effector closure of phones already is, it's not equal to humans, but it's very close, right? I mean, they can't mow the lawn, but they can do a lot of things that knowledge workers do. Partly I like to talk about that because it drives home the point that phones can do way more than they're currently doing. And then you start thinking about why are they not doing more? And a lot of it is because we want them to do idiosyncratic things that aren't built in. So that's kind of one reason that I like to do that. But it also, once you realize how many things they could do, you have to ask the question, how complicated a program do we need to teach it in order to do all those things? And even though Prolog is a Turing-complete programming language, and therefore if-then statements is a Turing-complete programming language, do we want some other constructs as well? I don't know. You had a question or a comment? No?
Well, I guess thought that kind of struck me was like, as we think about, I mean, it almost feels like this is democratizing programming to a certain extent. And then as that grows and as the machines learn and we learn, I wonder if there's a point where it tilts, where we're saying like, hey, teach the agent like we would teach a human.
Mm-hmm.
So I wonder if it also works the other way around.
That it would teach us?
Yeah, like what point does that like is that possible for them to do, like, because we're saying like, oh, teach them the way that we would learn, and if that's the way that we learn, then is it possible for that is it a way for us to get smarter or for us to get more efficient? Like, is there a way for us to like, I don't know, there's just like, it's just a thought.
That's interesting, and I hadn't really thought of it that way. Maybe I hadn't really thought about that question.
The machine's learning, then is there a way for us to accelerate our own learning based on if we tell them, hey, this is a problem I'm trying to solve.
Right. Or even explainability. So one of the topics that many people are concerned about these days is that we have these AI systems that can make decisions but not necessarily explain. And maybe if they've been taught by us, they will be able to explain in ways that are more like us. I don't know, but I think that's an interesting angle. I just I have nothing to say about it except it's an interesting angle.
So I think a related question, which is, if you could download skills, you know, in the Matrix you say, give me a program for flying some helicopter or something. if you could download a set of skills that had to do with traffic, a set of skills that had to do with snow, a set of skills that had to do with scheduling meetings, you'd only need some small fraction of the world's skill set.
Yeah.
And if those skills were things that you could then edit, learn from, and shadow with your own special preferences, maybe that's a sort of mixed mode where you would learn some things about scheduling meetings you wouldn't have even thought of because other people had thought more about it than you had. But maybe if your system then really does allow you to go into this dialogue, you'd actually not only learn things, but you'd very much quicker get to the kinds of things you actually want the system to do to make it personalized to you. Just a thought.
Yeah.
I think many years ago there was a project in Microsoft called Active Wizard. The idea here is basically supposedly you use Windows help menu, right? And it shows you, suppose you say, okay, open this tab, click on those, really, click on, and then execute that particular actions for you. And so next time, it's something very similar to this.
Yeah.
And then in the meantime, when it also shows that to the user, so next time you remember, right, you take those steps, and the next time I will do that myself. I can do that myself, right? So in those cases, you can also, you're teaching the programmer teach the computer, and then the computer will teach the user through those active wizards. Unfortunately, we didn't ship that.
Well, that's interesting. And over the years, there have been numerous efforts by people to do programming by demonstration, sort of teach a workflow to a system somehow. In fact, I'm told, and I even remember seeing that on my Apple computer, there is a similar thing where you can teach the computer a macro sequence of things you want it to do. An interesting question is, why have those things not caught on? And I mean, why am I not digging through my computer to find that functionality? The answer is, nothing comes to mind right off the bat of things that I want to teach it to do as a sequence, which is kind of interesting. Right? It's sort of like the Apple engineers have already figured out what's kind of the grain size of command. And maybe that's why I don't think, I want to open my email and then, I don't know, open my calendar. It doesn't seem like that wildly exciting to me. And so why do I think that doing it verbally on a phone would be more attractive to people than this? And I think part of the reason is I think it would be exciting is that people like to speak. People like natural language to communicate, and that's part of what's different here from learning macros. But I don't know, maybe I just like it because that's what I'm working on at the moment. But it is kind of a cautionary thing that these programming by demonstration things exist, and I don't use them at all, except in Emacs, where I still write macro editing commands. That's the only place where I still use it.
Okay, let's thank Tom.
Thanks. Thank you.